Okay, perfect. Now we're going to start our build session. So what we're going to be building? It's going to be a full DApp on midnight. We're going to talk about contract, API, CLI, and UI, where every action generates a real ZK proof. So what is this app about that we're going to learn? This is a single slot bulletin board, one message at a time. Only the original poster can remove it and force it by zero knowledge proof, not permissions. So far we've been learning how all the pieces within Midnight connect each other, and we learned a basic contract called counter contract. Now we're gonna increase the difficulty and we're gonna learn a contract called the bulletin board. So what we're gonna be learning in this chapter: how the compact contract defines secret circuits, how witnesses keep secrets local, how the shared API wraps everything, and how the CLI and UI consumes the same contract differently. The objective is to learn the architecture of the application and how pieces connect each other, and how the smart contracts are writing those ZKs, circuits, and then how we interact with the blockchain. Okay, so before we start, let's talk about architecture, how this application works. So for this, I have divided that in 3 layers. We have a layer 1, that is a smart contract, which is compact. We have a layer 2 for shared APIs, and the layer 3, which is the application. I have created this diagram where it illustrates in a better way the architecture. Let's go through that together. So for the layer 1, we have the smart contracts. We have the contract itself with the extension .compact. Then we have secret circuits. These circuits, for this contract specifically, we have 2 functions, 2 circuits. One is called post, and one is called takedown. Post, it's to actually post a message into the board, and takedown is to remove that message. Then we have the TypeScript bindings. After compilation, we get some contracts files. And we also have our witness files. So this is all layer 1. Then on layer 2, we have our shared API. So we have this bulletin board API that it's kind of the SDK of the contracts that is going to let us talk with the contract by using some SDK API that understands how to interact with the contract. So we have functions for deploy a contract, to join a contract, to actually run circuits. So in this case, it's post circuit, takedown circuit, and we also have some way to see the state in real time. So that's why it's dollar symbol, which means it's an observable. And then we have our layer 3, which is the application layer. In this case, we have 2 types of applications. One, it's on a CLI with a TUI, and then we have the React UI. So in the CLI, we use Node.js and LabelDB for our private information management, and our own wallet using the Midnight Wallet SDK. And for the React UI, we're using Vite to run the front end, and a Lace wallet. So in this case, our wallet is an extension on the browser that it's Lace. And for infrastructure, we are interacting with the proof server, the Midnight testnet, indexer, and the Lace wallet. As you can see, when we are using the React application, we are using the Lace wallet, and in the case with CLI, we're using our own wallet. Regarding the Midnight testnet, all these applications are now able to interact with different kind of networks. We have the preview network, pre-prod network, and soon the mainnet network. And at the end, I kind of show how this ZK proof flows, right? So we can understand it this way. We have the user action that runs a circuit, and here's a comment that says secret key enters via witness, never leaves your device. Then you create that ZK proof, use a media transaction with that proof, and if it's validated, then you have something that occur on chain. Okay, let's talk now about the ledger state. So the way we're gonna structure our data within the blockchain, the contract, it's using 4 variables. We have the state variable, the message variable, the sequence variable, and the owner variable. Each one, it has different types. We're gonna understand what these types mean and what they represent. So for the state variable, it's of type state. This is an enum which can have 2 values, vacant and occupied. So we have our bulletin board and it can have 2 states. Vacant, it doesn't have any message, and occupied, it means the board has a message. So the way we're going to represent those states is by using this ledger state variable of type state. Then we have another ledger variable called message, which is of type maybe of type opaque string. This is our message itself. And maybe represents that we can have that value or maybe we don't have that value. So it's optional. So in the right says the posted message or nothing. Then we have this sequence variable, which is of type counter. What this sequence means? This is everything that lives on chain. We have these 4 fields, and the sequence, as I mentioned, which is the counter, it's the clever bit. It increments on every takedown, which invalidates any proof generated for the previous state. So it's a way to actually reset the proof. So whenever somebody interacts with a contract, a proof is generated using that counter, which increments every time that anybody interacts with the contract. So it's really nice way to implement kind of a reset process for the proof system. And then we have this owner variable, which is of type bytes, which represents the owner of that message. Since we have a rule that only the owner is able to take down that message. So we need a way to have a representation of the owner. In this case, it's going to be a byte 32, which is a hash of the poster's public key. Okay, let's talk now about the post circuit. This is within the contract and it's specified by these following lines. We're going to understand what these lines means and what is the purpose of this circuit. So post, it's a circuit that is going to let us put a message on the board. So we have these assert conditions, and then we have some constants, declarations. Here's another declaration, and then here's some state change. So this assert, what we are doing with this, it's comparing things. We want to make sure that something is equal to something. That's assert. So in this case, we are taking a look at the state variable, and we want to match that with the actual value of the state, that's vacant. So if it's vacant, it passes. Otherwise, it fails. And when it fails, it says attempted to post to an occupied board, right? So that's why we want to make sure that it's vacant. If that passes, then I'm gonna update something on the ledger. But before updating something, that is this part of the code, I'm gonna declare some constants, variables, to actually update the state later on. So first, I want to define the new value of owner. And in this case, I'm calling a pure circuit, which is the public key. I want to get a public key from what? From a local secret key. This is a function that I'm calling a witness. In this case, our secret key. And then I'm grabbing the sequence. As we learned before, this is the counter that changes all the time when somebody interacts with that sequence. So the sequence plus the secret key and taking the hash with this circuit public key, what it does, it takes the hash. Then I'm gonna update the owner with that value. What I'm using this disclose, it's because I'm using some private information and I'm updating a public variable using some private information. If we hadn't used this hash over here, we could actually disclose this information, local secret key, because I'm putting something that is private into a variable that is public. But since it's a hash, we are protected in this clause. Even though we are protected, we need to make sure that we tell the compiler that we know what we are doing. And we do that by using this clause. So this clause, it's like, okay, I'm okay using this private information to update a public variable. Okay, then we update the variable message with what? With some new message. This new message, it's the variable that we are passing, a prop that we are passing to this circuit function, and we are using that and to update this message variable. We're using this clause again because we need to tell the compiler that we are okay to use something that it's been passed as a witness or as a variable, as a prop from a circuit to update a public variable. So with this clause, we're saying, okay, we are okay to do that. And at the end, we update the state variable with the new state, which is occupied. So after this circuit it's run, if another user tries to run the post circuit again, it's gonna fail because now the state has the occupied state. And this assert function is not gonna pass because it wants that to be vacant. Okay, so three things are happening here, just to kind of put everything together. We have this local secret key, which calls the witness. Your circuit key enters the ZK circuit, but never goes on chain. The public key that we're passing the secret key plus our sequence, it's a deterministic hash. Same secret plus the same sequence, same public key every time. That's why that sequence changes all the time whenever somebody interacts with the circuit. And then we have this close parameter function that explicitly marks what goes on chain. Everything else stays private by default. Okay, now let's study another circuit, which is the takedown. So we learned the post circuit, which actually makes it possible to post a message into the board, but now we want to take down that message. So for that, we have this circuit called takedown. We are not passing any props, and the output is going to be of type opaque string. Okay, let's understand what we are running within that circuit. First, we have an assert, where we are comparing the state that should be equal to the state occupied. So we want to make sure it's occupied to take down. If it's vacant, this circuit is going to fail with the message attempted to take down post from an empty board. Then we are doing another assertion. This time we are comparing the owner to be equal to the public key, which is the hash of the local secret key plus the sequence. This is the hash of the owner using the local secret key and the sequence. If the owner of that message is trying to take down the message, it's gonna pass. If a different user who is not the owner tries to run the circuit, this is gonna fail because that owner is not gonna be able to calculate the hash using its own secret key that gets the hash from the previous owner. Only the owner of the message has these secret keys and is going to be able to calculate the hash that matches this owner variable. So when it fails with a message saying attempted to take down post but not the current owner. Okay, if that passes, then we do the state changes. So in this case, we are declaring a constant called former message, and we're just passing the message, that value, which is the actual message that's the state that the bulletin board has. Now we're gonna update the state variable with a new state which is vacant. So okay, we have accepted that the user is gonna take down the message, so now we want to update the state to vacant. Then we want to increment the sequence. So whenever somebody interacts with a contract again to post something, when that happens, the sequence, it's going to be updated. It's going to be increased by 1. After that, we are resetting the message. How? We're just using this function called none. So now the string is going to be empty. And we are just returning the former message. So with circuits, we can update the state, but also we can return something so we can use it in our code. So in this case, we're just returning the former message. So that's why we need to declare this here as a return opaque string. So the assert line is where the ZK happens. The circuit proves you know the secret key that produces the on-chain owner hash without revealing the key itself. That's where the magic happens.